FEM or any kind of analysis. What is the need of that? Why we need to analyze a body? Just go for manufacturing any of the object, let's say a car or a table or a bench or any other equipment we have, just go for manufacturing it. Why we're needing to analyze that? First thing that we need to do the analysis. Why we need that? What is the need of it? That is over here. That is for your design validation. Okay, that is actually needed for your design validation, that the body or that figure which I am going to manufacture, that is capable enough to take the load which we are going to give them in the real world. If that is strong enough to take that load, then we'll go for manufacturing them. If that is not strong enough, in that case, what we will do, we will not going to do the manufacturing. We'll go for your redesigning it, or you can say we need to change something in the figure. Okay, so that we will see that yes, this body is okay, then after we'll go for manufacture, otherwise we'll not do it, that is known as your design optimization. That in your CAD softwares that we generally do, that is known as your what, that is known as your modeling, not designing. Actually people think that is your designing, but over here uh, designing is actually the combination of both CAE and your CAD. Okay, in the CAD modeling that generally we do, or you can say that is we generally model that figures. Okay, after modeling them, we generally say that yes, my designing is done, but actually not. That we have to go to your CAE software, any of the softwares. Over there, we have to validate that result. Okay, that in the real world, what it is going to feel. If that is strong enough to take that load, then only we will go for manufacturing. Okay, so that design validation actually going to show us in the form of the result, that is your stress, strain, deformation, or if that is your temperature, that is your heat, thermal expansion, heat flux, then pressure, velocity, this kind of mass flow rate, this kind of stuff we are going to see. Okay, but over here, you can see now this is now divided into three parts, three categories, or you can say three methods we are going to follow. What are they? Now over here, one is your analytical method, then numerical method, then it is your experimental method. Analytical method is the traditional method we generally use. Okay, that over here, this is the actually the traditional method. Traditional method means that anyhow we are going to use some amount of formulas, that theorems, like our mathematics we generally have some formulas, in physics also we have some formulas, that kind of stuff, stress, strain, deformation, everything has their own formulas and theorems. So we have to follow that theorems, that formulas, to analyze our result by using some pen and paper, like where we can do a sum, that 2 plus 2 that is equal to 4, but generally when we are going for higher kind of problem solving, in that case we generally use what, calculators. Okay, that kind of stuff over here, that hand calculations we are doing by using your analytical method, that is the traditional method. So over here you can see that analytical method also having some kind of advantages and disadvantages also. That advantage is what? Now over here anyhow we are going to get 100% accurate result, which is not possible in your numerical method. Okay, so over here anyhow you are going to get 100% accurate, but it has lots of demerits, that it is going to take a higher amount of time. Okay, if the body is not even, in that case we can't get the or you can say we can't get the result over there. Okay, let's say over here I have a rectangular body. So over here, let's say I have a square body. I need to find the area of it. Let's say this is A, this is A, the side A, and this side is A. So over here I can get that area as A square. Okay, but if I'm getting this kind of stuff, it does not have any specific size or shape or any specific dimensions there. So over here, getting your area is going to be very, very difficult for us. Okay. So so over here, we can't get your results for this body if I'm going for analytical method. But okay, and 100% accurate material conditions also we can't give to the body. Okay, so to overcome this kind of stuffs, now what we have that is known as your numerical method. Okay, to overcome that kind of stuffs, what we are doing, we're using your numerical method. Numerical method, what it is going to do? No, numerical method is actually a computational method we're going to use. That is, in short, you can say that over here we're going to use a software. That over here you can see that numerical method is a mathematical tool designed to solve numerical problems. Okay, that we're going to solve that problem that is known as your numerical problems. Okay, and the software we're going to use that is your called as a mathematical tool. Why so? Now, because over here, the inside the analytical method, that theorems, that formulas, that processes, everything are already given inside the software by using your programming languages and that algorithms. Okay, that programming languages and the algorithms, numerical algorithms were going to already given over there. So here it is going to give us that result very easily. Okay, that's why we're naming this as a numerical method. So over here, or you can say that is a mathematical tool. So it is not going to give us any headache or anything, but some advantages are there, some disadvantages also it is having. That in previous case, we saw that if the perfect uh, size is not given over there, that sides and all of these things are not given, so we can't get our result in our numerical, sorry, in your analytical method. But over here, there is a possibility for integration to get that result. We can divide this body in a number of parts. They say this rectangle can be done. Over here I can go for a triangular region, or here I can create a circle, or any kind of stops you can do to get the perfect result, or otherwise you can go for your integration so that you will get that result. But that process may take higher amount of time in your analytical method. But if I use your numerical method over here, that is going to take less amount of time for solving. Okay, in any kind of complex geometries, if we have that complex geometries are going to give us that result in your numerical method. Okay, so if your physical prototype is not present also, that is okay for us to get our result. But if we are going for experimental method, the over there anyhow we need our prototype. But over here you can see only one demerit is there, that is your approximate result we are going to get over here in analytical method. Anyhow we are going to get 100% accurate result, but in your numerical method what we are going to get the approximate results. Why we will see that? Because of your in numerical method, anyhow we are going to use to solve our processes by using your FEA or FEM. Okay, finite element analysis or finite element method. These processes are we're going to use in your numerical methods. So over here, this is giving us much more amount of advantages, but only one demerit is there. That is your approximate result it is going to give us. Okay, then over here you can see the next one is what? That is your experimental method. What is experimental method? Now, in experimental method, we are going to perform various kind of experiments to one body or to one prototype of the body which we are going to manufacture. This experimental method generally we are focusing on for components which is directly affecting to the human life, like your cars. Okay, because over here, what we're going to do now, over here, we're going to see the physical or some manufacturing errors are there are going to see that because over there, let's say we are having a two metal parts are there. Okay, two pipes, let's say two metal pipes I'm going to weld. So when I'm welding this region, so what will happen? So over there may be some air bubbles are there, maybe some part are not perfectly welded or some part are left out. Okay, so due to that reason, it is going to give us some other result. But these things were not considering in your analysis, that is in your numerical method or in your analytical method, we are not considering these steps. And if I'm giving that, you can say actual measurements we are taking. If I'm giving that measurement from here to here, it is 100 in the numerical method, that is, it is going to consider the 100, that means it is 100. But actually, when we are going for manufacturing it, anyhow, that length is going to decrease or increase little amount. A very, very little amount of this reason, it is going to increase or decrease. Okay. So that means what? 100% your length measurement is not possible always. Okay. So because of that, it is going to give us some other results also. Okay. Which is very crucial for human life. So if it is not crucial for human life, like your mouse or your phone or your laptops, this kind of stuff, if you are going for designing it, in that case, we don't need to go for your experimental method. Your numerical method is sufficient for that because your experimental method has lots of demerits in it. That it is very time consuming because over here we need to arrange lots of things. Over here we have to get 3 to 5 prototypes for manufacturing. So if I'm going for 3 to 4 prototypes, anyhow, that manufacturing process is going to take a very large amount of time. Manufacturing process is very high for 3 to 4 types. Again, it is expensive also. That manufacturing your 3 to 4 prototypes, it is going to take money. And when you are arranging all of the lab setups for the experiment, over there also that sensors, that dummy, if that is a vehicle, dummy human. So lots of things are going to be there. So that thing is going to take higher amount of money. So for due to that reason, maximum these stops were not going for your experimental method, but over here we're just going for where that is affecting your human life directly. In that case, we're going for experimental method. But over there, then before going for experimental method, again we have to go for numerical method. Okay, that we have to use your software or FEA for analyzing it. After that only we will go for your manufacturing. Why so? Now because your FEA, it is going to reduce your design cycle. If I'm going for FEA or that is called as a numerical method, in that case, it is going to reduce that design cycle. What is the design cycle? Now over here, let's say I'm designing a car, okay, or any chair, let's say. Okay, I'm having a chair over here. It has 4 legs. So when I'm applying a load at this region, I got to know about that over here, this leg is going to break because higher amount of deformation and stress is generating on this leg. So this leg is going to break. So I need to change something in that design so that its strength is going to increase. Either I'll change the design that over here I'll have a member stiffener over here, or I will change the material, or any other thing you need to do that, there. You just do this, and again you have to come back to the analysis. Over there you will analyze it. Again you will see that everything is correct. Then I will move out of this loop. But if I'm going for experimental method directly experimenting on this body, anyhow, it is going to give us the same result. And continuously in numerical method, in one shot, it is going to give us all the stress, strain, everywhere. It is going to give us that result. But if I'm going for experimental method directly instead of your numerical method, what is going to happen? Now over here, it may fracture some of the points. Okay, in different attempts, it is going to give us different result. Let's say I didn't change the material condition. I just went for giving a stiffener. but the stiffener is not the one. Actually, the problem is in your material you used. Okay, so again you have to go for your experimental method. Then again that you got to know that this plastic sorry, the material you are using, that is the problem. Then again you have to go back to the designing. Over there you change the material, or you can say manufacturing, again manufacture another chair by changing that material. Then again you have to go to your experimental method. Over there again you got some another problem, that the stiffener you need, that is also needed, that material should be a different one. So it going to be very, very time consuming and very, very expensive again for us, and the design cycle is not optimized. Okay, or you can say your optimum design you are not going to get in less amount of time. So because of that, what we need your numerical method, that is your FE or FEM over here. Okay, after that, we'll see that when your optimized result you got, after that you will go for experimental method. Then in that case, you will get in just one go, you will get your perfect result or that license from the government or anything. Okay. So because of that, our numerical method is very, very important for us. Okay. So that same thing we're going to do over here. So first of all, we'll see that numerical method over here, that is actually of four types. Okay, that numerical method we're going to see in the software or anywhere, that is actually divided into four types. What is that? Now, finite element method or finite element analysis, FEM or FEA, then boundary element method, BEM, then finite volume method, FVM, then finite difference method, FDM. So everyone has their own specific works. Okay, so for the let's say I have a car, okay, or you can say a movie hall we have. That movie hall sound is not going to come out from the uh, room. Okay, if you are standing outside your movie hall, then you are not going to see your sounds anymore, because that walls are optimized. Okay, that walls are designed in such a way or analyzed in such a way that you are not going to hear any sound outside the room. So that is actually done by your BEM, boundary element method. On the boundaries only, we're going to see the result, or we're going to generate your elements. So over here, then finite volume method to do your CFD analysis. Okay, any kind of CFD analysis you are moving through, that involves your finite volume method, FVM. So then when you are combining any of the three methods, that is any of the two in between three methods, that comes under your finite difference method. Okay, that comes under your finite difference method. Okay, so first of all, now what we are going to focus, now we're going to focus on your finite element method. What is finite element method? Okay, that is actually your finite element method or finite element analysis. That is actually your base of all of the three methods. Okay, it is the base, it is the fundamental part. Depending upon that, other three methods are involved, or they are now just having that finite boundary method, that is base is finite element method or finite element analysis. If you go for your FVM, in that case it is also that finite element analysis is the base one. If you are going for finite difference method, this finite element analysis is the base one. So depending upon that finite element analysis, FEA other are developed. Okay, so first of all, that what we are going to see now, finite element method is a numerical technique that we already know. That numerical technique for finding the result on boundary value problems. This is the key point where we're going to use FEA or FEM. That is the boundary value problems. What is that? We'll see. For practical differential equations, we are going to get, or we are going to use that finite element method. So this is also known as finite element analysis. So generally people get confused that finite element method and finite element analysis both are two different things. But in actual thing, that is both finite element method and finite element analysis. Both are one and the same. They are not two different things. Finite element method and finite element analysis both are one. Only because finite element method is actually developed by your university students, and they are using that term finite element method. But in industries, they just change that name, that is your finite element analysis, because they in the industries were using it vastly. In university they just developed it, but in the industries they are using it vastly. Okay, because of that they just change the name, that is your finite element analysis, because over here it is the base, and where you are solving our problem, or we're doing our analysis by using this method, so that, or you can say using this process and doing the analysis, so they just change the name, that is your finite element analysis. Okay, but finite element method and finite element analysis, FEM or FEA, both are one and the same. That what we are going to do in the finite element method, that is same as your finite element analysis, because like in your home you have a different name, in your school or colleges, in the practical world you have a different name, but you are the same person. In the same fashion, that this one is the same person but having two different names, finite element method and finite element analysis, but they are one and the same. Okay, so what is finite element method? Why we're using finite element method or finite element analysis? What is the need of that? Okay, so actually in analytical method or experimental, you can say that it is going to give us your result in one single particular body, not whole over the body. In experimental method, we're going to use sensors so that we'll get a result. But in experimental method, sorry, in analytical method, what we're going to do, we're going to get a result in one single point. But in your numerical method, that is your FE or FEM, by using that FE or FEM in numerical method, we're going to get your result whole over the body, that you can see over here. I'm getting my result whole over my body. Okay, so because of your FEA, or you can say that is your FEM. So what is the need of that? So first of all, it is saying that we're going to use that FEA when we're going to solve your boundary value problems. What is that boundary value problems? Let's say I have a box or a square body I have, and here I'm applying this one is fixed. Over here, this one is fixed. And I'm applying a force over here. One kind of force I am applying. Okay, or just take a cantilever beam. Or just take a cantilever beam. So this one end is fixed, and another end I'm just applying one force over there. So in this both of the cases, I want to see the result in it. Depending upon that problem, I want to see the result, that is maybe your stress, strain, deformation, all of these things I want to see. But what is boundary values? That boundary values means its one phase is fixed. That means is all degree of freedom on this point is zero. And another portion I'm applying some kind of force. In this case, I can apply some amount of momentum. Here, I can apply some kind of pressure. Okay, on this specific area, I can apply some kind of pressure. So this value, this problems, what I am getting, or you can say, here I'm having a rod. Here I'm applying some kind of temperature, and here also I'm applying some kind of temperature. And in this body, this point is fixed from here to here. And at this reason, I'm applying a temperature. At this reason, I'm applying a temperature. Different temperatures are there. So what is going to happen inside this body? So surrounding, I'm having a kind of temperature in this. This is your thermal analysis, and over here this is your structure analysis. Okay, in this case, one part is fixed. I'm having some kind of forces around in momentum. So these are your boundary values. Okay, these are my boundary values. If I'm getting this kind of stuff, then I will go for your finite element method or finite element analysis. So in this case, take this body over here. In this case, what happens? So when I'm applying this force is if I'm going for analytical method, I'll just pick one point, and depending upon that point, I'm going to get that result over that point only. But if I consider this whole body, how many points are there? How many points are there in this body? Any answer? How many points are there inside this body? How many? Anyone? If you are wrong, also it is okay. In this body, how many points are there? Inside this, how many points are there? Simple. That inside this, I have infinite number of points. Okay. If you consider that body, I have infinite number of points. So here, how it is going to solve? By generating your differential equations. So it is going to solve your result by generating some differential equations. So as I'm having infinite points around this body, how many equations it is going to generate? On this, if you consider your analytical method, on one single point, I'm applying the differential equation and I'm getting that result. In the same fashion, that when you are going for your infinite number of points, that equations are also going to generate for individual points inside it. So when it is it is generating your infinite points inside it, what is going to do? Now here I am going to get infinite equations. I have infinite points and I am getting infinite equations. So when you are getting that infinite equations in this region, then what will happen? It is going to take infinite amount of time to solve my result. Okay. So that means what? Indirectly, it is saying that you can't solve this problem. Okay, you are not going to get any result in this body. So what to do now then? So now I want to convert that infinite number of point to finite number of point. That you can divide this body, that it is saying what? Finite element method or finite element analysis. Finite. This is the key point, and over here, this is the key point. Okay, element. So that what does it mean? Now over here, that it has infinite number of points. So I need to convert it to finite number of points. Okay, I have to get finite number of points. How you are going to get your finite number of points? Now by generating your elements. Okay, by generating your elements, you can convert your finite number of equations or points to the infinite number of equations to finite number of equations. How? That same body I am taking, that over here I have that same body. How you are going to generate the elements? Now what I'm going to do, I am going to divide this body to n number of parts. Depending upon that, depending upon the figure, you will get n number of parts. Okay, that individual parts are known as your elements. So this is my one element. This is my another element. This is my another element. Okay. Over here, this one is my another element. Okay. Individually, you can see they are your individual elements. Okay. The intersection points of that elements known as your nodes. Let me change the color. That over here, this one, these points are known as your nodes. Okay, this one is a node, this one over here it is a node, this one is a node, over here this one is a node, over here this one is a node, so this one is a node. So that nodes are nothing but your points. Okay, these nodes are nothing but your points. Okay, So now I just converted my infinite number of points to finite number of points. Okay, that I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like that. I can count them. Okay, that is now I'm going to give my differential equations to these bodies or these nodes now. Okay, so that I can calculate it. Now you can ask, sir, how it is giving us result in between the bodies. Now, by using a mathematical tool or process, you can say, that is known as your iteration. Okay, by using your iteration, it is going to give us that the result at the middle of it or any of the points. Okay, that you are not going to do. That it is calculating the result on the bodies by a finite number of equations, and it is going to give us that result by using your iteration. Okay, so over here, okay, the due to that interpolation over here, I am getting that results. Okay, in between the bodies. Okay, so now this is your whole process of your finite element method, that over here I have infinite number of points, so that I am getting infinite number of equations, so that I am not going to get your body or result. Now I have to convert that infinite number of equations to finite number of equations. Okay, so that uh, how I'm going to get that finite number of equations? By generating your elements. Okay, by generating your elements, I'm going to get finite number of equations, so that I can analyze my body, so that I can do my analysis. Okay, understood? This is my finite element method, or that is my finite element analysis. So over here, inside this, these are known as your one elements. Okay, these are my one elements, individual. Whole over, if you consider that whole over the body, that elements which are generating, that is known as your meshing. Okay, whole over the body, the elements I'm getting, if you can say, just gather all of the elements, gathering that, you can say that whole over this is known as your mesh. Okay, and the process is known as your meshing. Okay, if we are just considering one body from here, one portion, it is known as your one element, and individual them, it are these are known as your one nodes. Understood? These are known as your one nodes. Clear? By using this, we are going to get our result. And over here, we have lots of other things are also there. That is known as your element that sorry these are actually divided into three parts. That element method, sorry, a finite element method is actually divided into three parts. What are they? Now 1D analysis, 2D analysis, and 3D analysis, or you can say 1D meshing, 2D meshing, or 3D meshing. Okay, the element it is going to generate, that for 1D it is going to generate a line only. For 2D it is going to generate a area element, it is known as your line element. For 2D it is known as your area element, and for 3D it is known as your volume element. Okay, for 3D it is known as your volume element. In line, your element shape is only one, that is your line only. But in your 2D, that is your area element, the shape can be of two types. One is your triangle, another one is your quad. Okay, it can have two element shapes or shapes. That is, one is your triangle, another one is your quad. For your 3D elements, we can have four. That is tetrahedron or tetra, then penta, then wedge. Sorry, penta or wedge, then hexa. That is, this is my hexa. Okay, this is my hexa. This is my penta. This is my penta. and another one is my pyramid. The shape is pyramid shape. Okay, these four shapes you are going to get for your 3D analysis. Okay, for 1D, one element shape is there, that is your line. For 2D, you are going to have that element name is your area element. Shape you are going to get, that is your triangle, and quad, that is your square element. Then for 3D analysis or 3D element method, that is 4, that is what? Now it is going to generate a tetramaze, a pentamaze, hexamaze, and your pyramid. This four element can be generated over here, that you can see over here. This is your hexamaze. Okay, over here you can see these are my hexamaze. Here these are my hexamaze, and over here these are known as your tetramaze. These are known as your tetramaze. This tetra quad, these are also going to be divided into multiple parts. Okay, depending upon the first order and second order, it is also going to divide into multiple parts. Okay, so this is my quad. This is my hexa. Sorry, if you go for 3D, it is known as your hexa, and this is known as your tetramaze. Okay, this type of mesh you are going to get over here, and this mesh I am getting over here. If I am considering the surface, everyone is a triangular mesh. Okay, here you can see in this one, everyone is a triangular mesh. If I'm going for inside the body, that is your volume, it is known as your what? It is known as your tetramesh. Clear? Or you can say that is your tetra element. So these things we're going to get your finite element analysis or finite element method. Because of that, we're working in your using your finite element method, or that is your finite element analysis. Simple. And also these are having some kind of qualities also. So because over there we need much more from some criteria are there for checking your qualities. Because if you are not getting good quality elements over here, you are not going to get good quality result. Anyhow, we are going to get your approximate results. But I need more accurate result. Okay, so to get more accurate result, anyhow, I need good quality mesh generation. That good quality mesh, anyhow, I need. So that good quality mesh, by checking that quality also, we can get your good results. One uh, uh, one good quality, how to check that is one is your aspect ratio. What is aspect ratio? Now, if I'm having an element, let's say I'm having a triangle or a quad element, let's say I'm having this quad element. Okay, this quad element, this is having 10, this is 2, this is your let's say 5, this side, this side is let's say 12. Okay, so how to check aspect ratio says that now it is as it is named as your ratio. So over here it is going to follow, it is going to be a division. Okay, so here I have to take the maximum edge length of the element, because here as I'm having a quad element, this quad is going to have four sides. So among of them, one side is going to be your bigger one and another one is going to be your smaller one. So here I am taking your bigger one is what? That is your 12, and smaller one is what? That is a 2. So here what I'm going to get? Now 6. So this is a very bad quality element. Not very, but this is a bad quality element, because the aspect ratio says that when I'm getting result aspect ratio as 1, that is the best quality element, or that is the ideal element. If I'm going for a perfect square, then every side is going to be a. So here if I'm going for a by a, what is going to get? Now 1, so it is the perfect one. But If you are getting result in between your 5, that is 1 less than 5, aspect ratio is less than 5, then this is acceptable one, because everywhere your 100% square meshes are not possible always. Okay, so because of that, if I'm going for getting aspect ratio, that value should have some limits in it. So that limit is that it should be less than 5. If I'm going for 5 or beyond 5, then this is considered as a bad quality element. So this kind of element checks are also we are going to consider in your finite element analysis. Otherwise, you are going to get a very bad quality result. Okay, understood? So now we will see this stuff inside your software. Okay, how we are going to generate your mesh, and I will just consider one body. Okay, and I will import that body, and we will do some analysis over there. So here I'm just closing it. So here I'm going for ANSYS. So it will open just for wait for some time. It will take little amount of time to open. So this is your ANSYS workbench. So inside this, we will solve our 3D problems. So it is opening. In between that, if you have any doubt, you can ask. Feel free to ask. If you have any doubt, you can ask. Okay, done. So I'm going for a static structural. So this is my ANSYS workbench, and over here this is my menu bar. Okay, and this is my tools, or you can say this. These all are my models. That from here I am going to solve my problems. Any kind of problem like modal solution is there, or static structural, static thermal, explicit dynamics, fluid, fluent. So this kind of stuff we are going to solve inside it. Okay, so let's over here inside this geometry, what I am going to import, I'm just importing a file. Okay, that a CAD file, I'm just importing it. Okay, done. I just imported my CAD file, and I need to solve it, or you can say I need to do the meshing, and I want to solve the problem. So that stuff I can do in the model. Okay, I'm just moving inside it. Okay, now import work is done. So what I'll do, I'll go for modeling, double click. So what will happen? Inside the model only, we're going to do our meshing. Over here in your engineering data, I'm going to give your material conditions. In the geometry, I'm going to import the body or going to create a body. And in the model that I'm going to give the forces or meshing or anything I'm going to do inside it. Okay, so here now you can see it is loading my figure. Okay, so here after certain amount of time I'll get this figure now. See, this is my body. Okay, so inside this meshing that FEA, I already said that FEA generally over here when saying that that is your mesh. So that is actually divided into two parts again. That is what local mesh. Another one is your global mesh. So over here, I'm just going to show you that here these are my global meshes. Okay, globally, I'm going to do this mesh that here I'm going for generating a fine mesh. Okay, and right click and generating that mesh. So by default, my software is going to generate your tetra meshes because over here I have lots of curves in it. So due to that curves, it is going to give us the tetra mesh. But I need, let's say I need hexa mesh. So for that, I'll go for your mesh control, mesh method. Inside this, I'm selecting this whole body, that geometry. Click on OK. And over here, I'm going for hex domain. Okay. Again, I'm just clearing the mesh data back what we created. That over here. Again, I'm generating your mesh. So now I'm going to get lots of amount of hex meshes over here, but anyhow you will have tetra, penta, and pyramid also, but quantity of your hex mesh is going to high. So it will take some amount of time because I am going to generate hex mesh. It is anyhow it is going to take higher amount of time, so no problem. Okay, so now you can see it is generating your code message, but I know that these code messages are not, I know that this quality is not good. But anyhow, I'm getting all of the code messages over here also. Okay, after generating your mesh, what I'm going to do, I'm going to give the boundary conditions to it. For example, what I'm doing now, I'm just saying that these holes are going to be bolted. That means what? These holes are going to be fixed. So I'm going to go for static structural. Over here, I'm going to give that fixed support, that load, that is your supports, that it is my fixed support. And inside this body and this figure, this one and this one are going to be fixed. That four faces are selected. They are fixed now. And at the backside of it, on this edge, I am applying a force of 500 Newton. That for that I'll go for load and force. That is not in the face. I have to go for your edge selection. That edge is this edge. Okay, in which direction it is moving. Now here applied. So here instead of vector, I'm converting it to components. That component over here, it is what? It is along y-axis. From these coordinates, I can see this vertical is my x. This one towards us is your, sorry, vertical is z. Towards us is our x. And in this direction, it is my y. So in this y direction, I'm giving how much? 500 Newton force. Okay, done, completed. Then what I'm going to do now in over here in your solve, I'm just going to okay, here before solving it, I need to give for what you want to solve it, because there are lots of criteria are there. So I need uh, to see the stress, I need to see the strain, and I need to see the total deformation of it. Then I'm going to right click and solve it body. So now it is going to solve my body, and it is going to give us that result in just less amount of time. Okay, it is saying us some error. So 1 second, let me see. It is not solving. So over here, that force which I applied, that is actually not perfect in this case. So I'm just taking that force instead of your edge. I'm taking your face for this site. I'm just taking its face, but also it is not going correct. Okay, let's okay, in this condition, for sometimes it happens that over here I'm going for 5 or 1000, let's say. Okay, and direction is this direction, that opposite of it, done, apply. But also this is static structural is not perfectly applied, I think. Okay, we'll see that. Okay, that over here everything is perfect, but because of the software issue, it is not getting us result. 1 second, it is not going to give us that result. That over here I'm applying that force in this direction, in the y direction. These two supports are fixed, but it is not giving us result because of that bug I have over here. Okay, so for that issue, it is not able to solve my result in this case. But after turning off and on, it anyhow it is going to give us that result. Okay, so let's go for instead of giving lots of data to it. Okay, I'm just going for deformation. No, that solver problem is there. Okay, for that again I have to close it, and again I have to open it. But anyhow, the process which I followed, that process is from start to bottom. I have to follow that process so that I will get my perfect results. Okay, so as we have less time now, so I'm not again doing that same thing, but the process I just followed, that process is going to be same for everything. Okay. So now if you have any doubt, you can ask.
Absolutely. So, student, as sir has already told that we will having a less time for Q&A. So, quickly, any doubts in today's curriculum? I think it was very well articulated on the theoretical aspects, because previously all the sessions on FEA I had and we had were directly focused on directly for the practical, because this was a very informative sessions about the theoretical aspects. So I hope all of you could follow through the whole sessions. So Aditya, Aniket, Mohan, Alphonse, Harigopal and Vijay, if you have any doubt or you want to add anything to the sessions, it would be appreciable. So you can also raise your hand to ask the questions.
Feel free to ask.
Sir, I think all the questions, and I think they don't have any doubts. So we can move on with the sessions and call it a day. And thank you, sir, for joining and enlightening the students, because this session was very helpful in terms of they got to know about the theoretical aspects. So I hope we will see all of them on the other side. And thank you, sir, for joining.
Thank you. So then I'm leaving this section. Thank you all for having me.
Absolutely, sir. Absolutely. Have a good night, sir.
Good night.
So, with this, I think we are at the end of the sessions. So, any doubts you want to ask? I guess not. So, thank you all. So, good night to everyone.